All right. Welcome, everyone. Get going today. So today we're going to finish up chapter 15 on chemical equilibrium. Now that doesn't mean we're going to be done talking about chemical equilibrium. We're just going to be finishing up the general aspects and ideas of chemical equilibria, and then we'll be applying chemical equilibria and these concepts and ideas to specific problems, specifically first talking about acids and bases and acid-base chemistry, and then we'll talk about solubility of compounds and that relationship with chemical equilibria as well in chapters 16 and 17. Okay. And so, right, as a reminder, there is a quiz on Canvas that is due Friday evening. It's going to be available starting Thursday afternoon. And then the homework for chapter 15 is due by Monday at 10 p.m. Okay. Are there any questions people have about anything related with the course, whether it be course material or just how things are structured or what's happening in class in general? Yep.
What's the key for the passage exam?
Yeah, I can post some type of exam key. I'm kind of looking into how I do it because I have multiple versions of the exam with different questions on different versions. So, but yeah, I will look into trying to do that and get that up by sometime this week. Other questions? All right. So the last bit of stuff that we have in chapter 15 are going to be doing these ice problems, these equilibrium problems, talk plenty about, and then we'll also talk about the Liège principle. Okay. So we're, like I said, in this chapter, in chapter 16 and chapter 17, we're going to have plenty of problems. We'll end up with some sort of chemical reaction that is an equilibrium reaction. Okay, so let me just go here. Right, so for those in class, right, if you didn't grab the handout, there's the example questions already printed out in the back by the door. All right, but so we have this very first question. We'll do this one together so I can talk about and explain how we approach these equilibrium problems, and then give you guys time to work on, say, the next one by yourself before we work out the answer together, okay? But this one we'll just start right away and discuss how we approach this, right? So again, when we read the problem, okay, we have this decomposition reaction of SO3 going to SO2 and O2 gas, okay? I know, right, so initially my container, which is at 1,000 degrees Kelvin, has a partial pressure of 0.5 atmospheres of SO3 initially, okay? And that's it, right? If you're not told any other pressures, that means there's nothing else in there, right? So I just have SO3 in this container, and then I'm also told at equilibrium, the partial pressure of SO3 is 0.2 atmospheres, and I want to know, well, what is the value of the equilibrium constant, okay, for this reaction at 1,000 Kelvin? Okay. Right, and so again, in this problem, I see it's an equilibrium problem relating with concentrations or pressures and equilibrium constant. Okay, so an equilibrium problem relates to equilibrium constant and concentrations and pressures, and specifically looking at the equilibrium concentrations or pressures of different species in your reaction. Okay, So that's telling me it's some type of an equilibrium problem, okay? So what I want to do, SO3, shoot. Use a new sheet of paper. Right, so I want to write out my chemical reaction. 2SO3 gas going to SO2 gas, and we'll see why I'm rewriting the chemical reaction in just 1 second, plus O2 gas, okay? And so what I'm going to do in these type of equilibrium problems is create what's called an ice table or an ice chart, okay? ICE, okay? I, this stands for the initial values, C is the change, and E is the equilibrium concentrations or values or pressure, right? And so in this problem, okay, I'm told, right, that initially I have 0.5 atmospheres of pressure of SO3, and then I have none of O2 and SO2, okay? So in this problem, I just have reactants, right? So this reaction, in order to reach equilibrium, is going to consume some reactants and form products, right? There's no way it can consume products to form reactants because there are no products to consume. So I'm going to lose some amount of SO3. Now what I'm going to do is I'm going to multiply this by its stoichiometric coefficient, okay? So I'm going to lose 2x of SO3, where the 2 comes from its stoichiometric coefficient. That means I'm going to gain 2x of SO2, and I'm going to gain x of O2, right? So these changes are based off of the balanced chemical reaction, where I multiply by the change by the stoichiometric coefficients. And again, I don't know how much is changing right now, but I do know to reach equilibrium, right, my chemical reaction is going to use up some of my reactants and form some of my products, okay? And so at equilibrium, the equilibrium value is just going to be the initial value plus the change that occurred, right? So 0.5 minus 2x, 0 plus 2x, and 0 plus x, right? So this is just, right, 2x, and this is just x, right? So those are my equilibrium values, okay? Now, we're told something else in this problem. We're told that the pressure of SO3 at equilibrium is equal to 0.200 atmospheres, right? Let's see if I can, that looks a little bit better. All right, so again, we're told, right, at equilibrium, the pressure of SO3 is 0.2 atmospheres. Okay? So we know what that equilibrium pressure is. But according to this ice chart, right, the equilibrium pressure is going to equal 0.5 atmospheres minus 2 times the change, okay? Right, because again, this is the equilibrium pressure of SO2. So I know that 0.2 atmospheres equals 0.5 atmospheres minus 2 times my change, which I'm just calling x, okay? And now I have this equation that I can use to solve for x, right? So I just solve for x, add 2x onto the other side, subtract 0.2 over here, right? And you get 2x equals 0.3 atmospheres, okay? Divide both sides by 2, right? You get x equals 0.15 atmospheres, okay? So that is our change, right? So that's our change. And why are we doing all this, okay? I guess I should have, said from the beginning, right, why the heck do we care about doing all this, right? In the problem, we're asked, what is Kp equal to, right? What is the value of Kp? Well, we're not told it, right? We need to find it. To find the value of Kp, we need to know what the equilibrium pressures are of our reactants and products, right, putting this EQ here to specify equilibrium. Right? So to get Kp, so let's just take a step back, right? So why the heck did I do everything I just did? Okay. This is what we're asked for. What is the value of Kp? What does this equal? Okay. Well, I don't know what the equilibrium pressures are of SO2 and O2 right off the bat, right? I'm told, hey, the equilibrium pressure of SO3 is 0.2. Great. I can plug 0.2 into here, but I have no idea what the equilibrium pressures are for these guys. Okay. Right? I got no clue, right? And so that is what we're trying to find out. We're trying to find out what is the equilibrium pressure of SO2 and O2, so I can plug all those pressures back into my Kp expression to then get a numerical value for Kp. Okay, so that's the thing, right? To calculate Kp, right? What is the numerical value of Kp? So again, going back to what we were doing here, right? So again, I set up this ice chart. Ice chart is my initial, my change, and my equilibrium value. Equilibrium is just the addition of the initial and change together. My change is always going to be some x value multiplied by stoichiometric coefficients. Typically, right, if we just start with reactants, then I'm going to lose reactants. Okay. And then in this problem, I'm told the equilibrium pressure of SO3 is 0.2. And so I know that 0.2 has to equal 0.5 minus 2 times the change. And so we get that the change is 0.15. And so finally, right, I know the equilibrium pressure of SO2 is 2 times X. So that tells me P SO2 at equilibrium equals 0.3 atmospheres. Okay. And P of O2 at equilibrium equals 0.15 atmospheres. Okay. So again, I know that these are 0.3 and 0.5 because I plug X into the values up top, right? I have my chemical reaction here. I'm going to manually zoom out just a little bit, give myself a little more room. There we go. Right? So we have, right, our chemical reaction, right? These are the pressures of SO3, SO2, and O2, right? So this is the equilibrium pressure of O2, which is just equal to X. The equilibrium pressure of SO2 is equal to 2X. Right? And the equilibrium pressure of SO3 is 0.5 minus 2X, which we know has to equal 0.2. Okay? So again, that's how we solve for X by using that bit of information provided in the problem. Okay? And then once we have X, we can find the equilibrium pressures of SO3 and O2, right? And so finally, right, plugging in, right, those equilibrium pressures into our Kp expression, right? This is going to be equal, so the equilibrium pressure of SO2 we determined was 0.3 atmospheres. So that's 0.3 squared, times the equilibrium pressure of O2 is 0.15, divided by the equilibrium pressure of SO3, which is 0.2 squared. Plugging that all in, you get that Kp equals 0.338. That is the numerical value for Kp for this problem. Okay. All right. So again, right, the problem itself is talking about an equilibrium reaction that's relating Kp with pressures or concentrations, right? Your equilibrium constant with your concentrations and pressures at equilibrium. That tells me, right, before I even write this out, I know somehow in this problem I'm going to have to use these ice tables, okay? And to set up the ice table, I write out the initial values, which are typically given in the problem. I write out what the changes are, and then I get the equilibrium values by just adding the initial and change together, okay? And then in this problem, I'm told that my equilibrium concentration or equilibrium pressure of SO3 is 0.2, so I use that to figure out what the change is, and then I plug in that change to get the equilibrium pressures of SO2 and O2. Okay, and then finally plug back into the Kp expression here. So, all right, so questions about how we did this, why we did this, where we got this number or that number, or other things. Okay? It'll be the first of many equilibrium problems that not only we'll do together in class, but you'll have to do on homeworks and exams and things of that nature. Okay? So, all right, so how do you know when to put negative and positive values in the ice chart? So specifically talking about the change, okay? So in this case, it's fairly obvious that the negatives are the reactants and positives are the products because I have no products initially. So I can't lose some amount of products if I don't have any to lose, right? So the products have to have a positive change, which means the reactants have to have a negative change, right? And you know, if the products are positive, the reactants are negative. If the reactants are positive, the products are negative, right? They have to be opposite sign, right? It's a chemical reaction, right? If I'm losing one thing, I got to gain the other, right? I can't gain products and reactants at the same time. That's not physically possible. Now, if the problem was designed to where I had no SO3 initially and some initial pressures of SO2 and O2, then I would have some negative value for the products and some positive value for the reactants, right? And most problems that you'll deal with will have that be the case where you'll either have no products or no reactants, and it's very obvious which way the reaction goes, right? Which sign you need for your change, whether it's minus in the reactants or minus in the products. If you don't know, then what you can always do is given your initial values, let's say I had some problem where I had, you know, an initial, let's write out the reaction here again, SO3 2, going to 2SO2 plus O2. Let's say initially I had, I'll say 0.3 here, 0.5 here, and 0.1 here for my atmosphere, right? ATM. These are the different initial pressures, right, of my gases, right? And the question is, what direction is the reaction going to go? Okay, to figure that out, we have to do something like what we did at the end of class last time, where we need to calculate Q, the reaction quotient, and compare it to K to figure out whether or not I'm going to form more reactants or form more products. And based off of that, I then know whether or not I have minus X here, right, or if it's minus X over here, right? So depending on the value of Q, right, which in this case Q would be the pressure of SO2 squared, 0.5 squared times 0.1 over 0.3 squared, okay? And I'd calculate this out and see is Q greater than K or Q less than K, right? If Q is greater than K, that means I will lose products, right? And I'll gain reactants. If Q is less than K, right, I will lose reactants, right? I'll gain products, right? Depending on how big Q and K are. Sorry, that was kind of off to the side, right? So most problems, the sign of X or not, we have to, you know, do minus 2X or plus 2X here. It's going to be obvious based off of whether or not I have any amount of products or reactants available, right? But sometimes it might not be straightforward, and so you have to calculate Q to figure that out. Yep.
Did you put inverse of like the student essay just because like it's going to be used up? Because we did put the inverse of the other like the SO2 in there.
Inverse.
You said something about taking the inverse of like the coefficient in front of like the SO3.
If I said the word inverse, I said the wrong word. I use the stoichiometric coefficients here from the balanced chemical reaction. But yeah, I mean, nowhere here do we use like the inverse of something. So I must have misspoken if I said something about that. So yeah, we use, right, the stoichiometric coefficients in our chemical reaction to determine the constants that we multiply our change by in the change, right? 2, 2, 2, 2, 1, 1, right? But yeah. I guess maybe like if I maybe said something about like you use the opposite sign, inverse of the signs, right? If you have negative over here, it has to be positive over here. You have negative on the products, it has to be positive in the reactants. Other questions? All right. So, and take a minute, work by yourself or with others if you prefer. So look at this second example here, where I have a 1 liter flask filled with 1 mole of H2, 1 mole of I2 at 448 degrees Celsius. And I know what is the value, or what's here? Oh, not what is, right? You're given the equilibrium constant for this reaction is 50.5, right? So this 50.5 equals K, right? So 50.5 is the equilibrium constant K, right? For the equilibrium reaction, H2 plus I2 going to 2HI. And the question is given those initial amounts of H2 and I2, what are the equilibrium concentrations of H2, I2, and HI in moles per liter? All right. So look over how we can answer this question, okay? So again, in this question, we see a problem where we're dealing with an equilibrium reaction. We have some equilibrium constant, and we're looking at equilibrium concentrations. So that tells me I'm going to need to use an ice chart. And I'm also going to need to write out, right, what does my equilibrium constant equal in terms of these concentrations? Right, it's going to be equal to what? What's the expression for K equal to?
50.5.
HI squared over H2 times I2, right? So that's my expression for the equilibrium constant K, right? We also know that K itself equals 50.5, right? So this thing equals 50.5, right, given in the problem. Okay. And then, right now, in order to find the equilibrium concentrations, I'm going to need to use this equilibrium constant as well as an information we can get from making this ice chart. Okay, I'm going to do ICE. I start off with 1. So it's 1 mole per 1 liter. This is 1 molar, and then I have none of this. Okay. So note that in these ice charts, we want to be using concentrations and pressures. Okay. So if, right, the volume wasn't 1 liter but was 2 liters, then I should be dealing with 0.5 molar, 0.5 mole. Right. I have to calculate the concentrations of our gases or aqueous species or their pressures, depending on kind of what's given in the problem, right? So, right, I don't want to use moles. I want to use concentrations or pressures. This is important to just emphasize now, because later when we talk about acids and bases, and when eventually we talk about titrations, it will be very important to make sure you're using concentrations instead of moles, which sometimes are given in the problems. Okay. So anyway, so this is my initial change, or my initial amount, right? So what's my change going to be? Minus X for H2, minus X for I2, and plus 2X, right, for HI. Stoichiometric coefficient 2, gain 2 here, right? So the equilibrium values are going to be what's the equilibrium value for H2? The expression for it. What do I put in for the E here in this chart? Yeah, 1 minus X, right? 1 minus X and 2X, right? The equilibrium is just the sum of the initial and the change. I just add up the initial and the change to get the equilibrium values, okay? And so those are my equilibrium concentrations of H2, I2, and HI, okay? But obviously, I don't know what X is, but I have this expression up here, this equilibrium constant, that can help me figure that out. So that equilibrium constant K, which equals 50.5, equals the equilibrium concentrations of HI squared over H2 and I2, which is going to be 2X squared over 1 minus X times 1 minus X. Okay? Right, which this gives me then an equation involving X that I can solve for to find out what the numerical value of X is. Now, before I start solving this, I'm going to rewrite this equation just a little bit and write this as 1 minus X squared. Okay. And I'm doing this because this is basically just 2X over 1 minus X, all of that squared. So 2X squared over 1 minus X squared is the same thing as 2X divided by 1 minus X, everything squared. And so I wrote it like this because in order to solve for X, I can simplify things a lot by writing it like this and just taking the square root of both sides. Okay. So I have, 2x divided by 1 minus x squared equals 50.5. So if I take the square root of 50.5 and the square root of 2x divided by 1 minus x squared, that's going to give me 2x over 1 minus x equals the square root of 50.5. Should I write down what that number comes out to be? Shoot. No. What's that number? This equals 7.11. I'll just round it there. Okay. And so then now I can use this equation to solve for x. So I multiply 1 minus x over, okay, and we get 2x equals 7.11 minus 7.11x. Okay. Grab a piece of paper here to continue on with this, right? So, okay. So again, I'm trying to solve for x here, which is my change. So now I add 7.11x to both sides, right? To get 9.11x equals 7.11. And then finally divide by 9.11 on both sides. And that gives you that x equals 0.78. That's going to be like molar, okay? So that's our change, right? So we find the change, right? So then I can plug this change all the way back into my equilibrium expressions, right? So that the equilibrium concentration of H2 equals 1 minus x, which equals 1 minus 0.78. So, right, that equilibrium concentration of H2 then just equals 0.22 molar, right? Similarly, the equilibrium concentration of I2 is going to be that 0.22 molar. Okay? It's because they're the same, right? They're both just 1 minus x. And then the equilibrium concentration of HI is just equal to 2 times x, which again, plugging in x is 0.78. That's 2 times 0.78, right? So the equilibrium concentration of HI, I saw on the screen, yeah, just barely, equal to 1.56 molar. Okay. So finally, I have my equilibrium concentrations of all of my species, right, which is what we're asked for in the problem, right? What is the equilibrium concentration of HI, I2, and H2? And that's it. 1.56 for HI, 0.22 for H2, 0.22 for I2. Okay? So for solving these type of problems, when you get to this stage here where you're plugging in the equilibrium concentrations into this expression for K, right? On the homework, I think there might be one problem, maybe two, where you have to use the quadratic formula on the homework. On quizzes and exams, you will never have to use the quadratic formula to solve these things, right? So just keep that in mind that you'll never need to use the quadratic formula. You don't need to remember what it is. Whenever you learned it, okay, we won't, when doing homework, you can look up things online, use whatever you want to help solve whatever math problems and things like that pop up, okay? But again, in class, on exams and such, you will never have to use this quadratic formula, okay? to solve these things. Okay. So questions about how we did what we did, why we did what we did, where did we get certain numbers, where did we start, why did we start?
So anytime you give two values for, so I give values for H2 and I2, but not HI, we just put 0 at or any measurement like that.
Yeah.
It doesn't give you a value.
Yeah. If it doesn't tell you there's some initial concentration, that means there isn't any. That means it's 0. So yeah. So if it doesn't tell you in the problem what the initial concentration is, then it is 0. It's not even an assumption that it's 0. It is 0. It's specifically mentioning that there's none in there, right? But yeah. Okay, so explain the 0.22 again. Right, so to get the equilibrium concentrations of H2 and I2, right? So in this ice chart, right, another blank piece of paper here. Let's use this. Just in general, let's say, I'll write that reaction, okay? Again, H2 plus I2 going to 2HI, right? In these ice charts, ICE, right? This thing here is the initial concentration of H2. I'll call it H2 naught, right? We've used that term before in kinetics, right? The initial concentration, okay? It's the initial concentration of I2 and the initial concentration of HI, right? And then at this E column, these are going to be the equilibrium concentrations of I2, H2, and HI. Okay, right? So whatever we get in the E row of our ice table here, okay, those are the equilibrium concentrations, right? So if the problem is asking for what is the equilibrium concentration of your species, right? You're trying to solve for these things, right? You're trying to solve for what's in this row, the equilibrium row on your ice chart, okay? Which in our ice chart here, right, the equilibrium row says the equilibrium concentration of H2 is 1 minus X, okay? So here I'm going to get rid of like kind of how we solve for X real quick and just focus on X is 0.78, right, after we solve for it. And so the equilibrium concentration of H2 is 1 minus X. We know that based off of our ice chart. And so I do 1 minus 0.78, which gives us 0.22. And then similarly, the equilibrium concentration of I2 is 1 minus X, which is 0.22, as we just showed. Right? So that's where we get the 0.22 from, okay, for these equilibrium concentrations, is because based off my ice chart, I know the equilibrium concentration of H2 is 1 minus X, equilibrium concentration of I2 is 1 minus X, and the equilibrium concentration of HI is 2X. And and then I use my equilibrium constant expression here, K, in order to solve for X. Other questions? All right. So for this third example here, these ice charts, okay, we're going to set this one up. But so this example here, I have more for like when you're going over homework to check that you kind of do things right. Basically, in this example, you would have to use the drop my pen. You would have to use the quadratic formula to solve for X here. Okay. Again, I'm not going to go into using quadratic formula and things like that in this class because you won't have to do it on exams and things like that. But we'll set up the problem and set up everything as to how you'd solve for x to kind of get the answers. And then you can use this kind of as a reference. If on the homework you need to use a quadratic formula, to see, okay, I used it correctly on this problem, so I know I'm using it correctly on another one, right? But so for here, you're welcome to solve for the equilibrium pressures, but if you want to just basically set up the problem, set up your ice chart, we'll start with that, right? So I'll even kind of write things out for us. Okay. So take just a minute to write out what, to fill in this table, basically, this chart. All right. So at least, again, talk about how we fill in this chart. So what is going to go for my initial value of PCl5? At 1.66, right? And then what about PCl3 and PCl2? Zero, right? And so what's my change going to be for PCl5? Minus x, PCl3, x, and PCl2 is x. So the equilibrium values right, again, initial plus change, so 1.66 minus x, and x, right? So then solve for x, we use our Kp expression, the 0.497 equals pressure of PCl3, which is x, times the pressure of Cl2, which is x, divided by pressure of PCl5, which is 1.66 minus x, okay? So again, if you then solve for x here, right, you'd multiply 1.66 minus x over here, right? Get like 0.497 times 1.66 minus x equals x squared, okay? and you know, move things around, use a quadratic formula to solve, okay? If you do that, I'll just kind of give the answer here. X ends up being 0.693 atmospheres, okay? So X is 0.693. And so then we know the pressure of Cl2 at equilibrium is just equal to X, which is 0.693 atmospheres, right? Pressure of PCl3 at equilibrium is equal to, again, 0.693 atmospheres. And then the pressure of PCl5 is equal to 1.66 minus 0.693, which this equals, I don't have that number written down, 0.97, roughly. If I did my math right. I don't know. Seems right-ish. 796, yeah. More or less rounding, 0.97 atmospheres. Okay. And so these are equilibrium partial pressures, okay? Again, here you'd have to use a quadratic formula to solve for this. I'm not going to go over it kind of in class because it's not really relevant to quizzes and exams. And there's like, you know, solvers online and things like that. While you're doing the homework, you can always Google and use and such. You know, and so I'm not going to kind of go over doing that here in class and taking time to do it. Okay? But I will ask, are there any questions about how we set up the ice chart once we knew what the change was, right? How we got the equilibrium values, how we set up this relationship, whether or not, and not necessarily how we solve for X, but how we set this up, right? There's, in each of these problems, there's three kind of steps. There's setting up our ice chart. There's using our ice chart and our expression for Kp to solve for some unknown variable. And then often finding then what the equilibrium values are by plugging in that change back into the final row of our equilibrium chart here to get the changes. Okay. Okay, so we will finish up today talking about Le Chatelier's principle. Okay. So what is Le Chatelier's principle all about? What is it saying about equilibrium reaction when I do something to it? Yeah, right. So, So in equilibrium reaction, if you disturb it, right, you move it away from equilibrium, it will shift by either forming more reactants or form more products to reestablish equilibrium. Okay, right? Le Chatelier's principle is basically just stating every chemical reaction wants to eventually reach equilibrium. So if you pull it away from equilibrium, it's going to go back. Okay, right? And so the question then, right, we can ask is, what are the different types of things that we can do to affect our equilibrium, right? We have some general equilibrium reaction. Okay. I'm going to do some very simple type of reaction here. 10-item chemical reaction. 2A gas going to B gas, okay? And I'll even say this is an exothermic reaction, okay? So given this information, we can ask different questions, like what happens when I add A gas to my vessel. What is my equilibrium reaction going to do if I add a bunch of A into my vessel if it's already established equilibrium, right? So let's pretend, right? Pretend you have this chemical reaction has reached equilibrium. I'm now going to add more A into the reaction vessel. What is it going to do? It's going to shift to the right, which means, right, it's going to form more products, right? I've added in extra reactants, which has taken it away from equilibrium. So it's going to use up some of those reactants that you added to reestablish equilibrium, right? This will shift to the right. Okay. What about when I remove some of B? Right? If I remove some of my product B here, what is going to happen? Huh? Yeah, same thing. It will shift to the right. Okay? Right? Because what you've done is you've removed some of your product, so your equilibrium is going to try to replace some of the product that you've removed. Okay? Right? So when you're adding or removing some amount of reactants or products, your equilibrium shifts either to the left or to the right to either consume some of that extra stuff you've added or to create more of some of the stuff you removed, right? So if I removed a reactant, it's going to create more reactants to compensate for what you've just done, right? If I add in products, it's going to consume some of those products in order to compensate for what you've just done, right? And then we use this term shift to the right, right? If it shifts to the right, you're creating products, right? Right, that's what that means, right? Shift to the right means form products. Shift to the left means you're going to form reactants, okay? So adding A will shift it to the right. If you added B, you'll shift it to the left, right? When you remove B, you shift it to the right. Remove A, you shift it to the left, right? So when you add or remove some amount of a concentration of, you know, a gas or an aqueous species, right, of reactant or product, your reaction is going to try to undo what you've just done, right? Again, if I add something, it's going to try to undo that by using some of it up, right? Reacting some of it up. If I remove something, it's going to try to undo that by creating more of what you just removed. Okay? And now temperature, what happens when I increase temperature? Right? An increase in my temperature for this reaction is exothermic. Yeah, so this is going to shift to the left. Okay. Now, how you can think of that for a chemical reaction is, okay, the enthalpy here tells me this is exothermic, which tells me heat is a product. So I can think of heat as a product in my chemical reaction. Or I could think of this as temperature, right? Heat is a measure of kind of average kinetic energy, things like that, right? So when I increase my temperature, I'm adding heat to my reaction. That's like adding a product, right? And as we just talked about, if you add a product to your reaction, it's going to consume some of that product and shift to the left to form reactants, okay? So in this case, increasing temperature shifts it to the left. Now, if my reaction was endothermic, right, I had a positive enthalpy change. It was endothermic. Heat wouldn't be a reactant. It would be wouldn't be a product. It would be a reactant. And then increasing temperature would add reactants, and it would shift it to the right, right? So how temperature affects the equilibrium depends on whether or not your chemical reaction is exothermic or endothermic, okay? But again, as long as you think of exothermic means heat is a product, endothermic, heat is a reactant, then increasing or reducing temperature is the same thing as adding or removing a reactant or a product. Okay? And then for this chemical reaction, if I increase pressure, what will happen to this reaction? It will shift to be right. Exactly. Okay. So how pressure and similarly volume is affected by this, right? So an increase in pressure is the same thing as a decrease in volume. Okay, right? If I have a gas, I decrease its volume, its pressure increases, right? Goes back to ideal gas law and things like that talked about in Gen Chem 1. Okay, right? So if I increase the pressure, right, my chemical reaction is going to go in whatever direction has fewer molecules in the gas phase. Okay, so in this case, I have one molecule in the gas phase on the product side. I have two molecules in the gas phase on the reactant side. So in this case, as I increase pressure, I'm going to shift to the right to form more B, because what that's going to do is that's going to decrease the net amount of molecules in the gas phase, which is going to lower the pressure. So again, you increase pressure, your chemical reaction is going to do something to try to reduce the pressure back down. And the only way it can do that is by forming fewer gas molecules. And to do that, it then shifts to the right to form more products, right? And the same thing about the decrease in volume. The decrease in volume corresponds to an increase in pressure, okay? So a decrease in volume means you want to form, right, whatever side of the reactant, whatever side of the equation has fewer gas molecules, right, because there's less space to hold those gas molecules, right? So again, you just, right, remember that increase in pressure is the same thing as a decrease in volume. Just like a decrease in pressure is the same thing as an increase in volume. Things are interchangeable with each other. Okay? And then what about if I add a catalyst to this reaction? What happens? So for a catalyst, sort of a trick question, nothing happens. Okay? A catalyst brings you to equilibrium faster, but it does not affect equilibrium at all. So you add a catalyst, it will not change your equilibrium, it will not shift to the left or to the right, it will stay where it's at. It just makes it reach equilibrium faster. Okay?
So catalyst and equilibrium reaction affects the forward and the reverse?
Yeah.
Reaction?
Yeah, because if we, right, so we talked about catalysts with this kind of activation barrier stuff, right? Well, if the catalyst lowers the activation barrier, right, in the forward direction, it also lowers it, right, in the reverse. Okay. So yeah, so a catalyst will lower the activation barrier for both the forward and the reverse by the same amount, which will mean it's going to increase the rate for the forward and reverse by the same amount. Mm-hmm. So questions about this?
Whenever you're increasing pressure for reactions to more products, it would
So yeah, so if you increase pressure for a reaction that had more gas molecules on the product side, is that right? That's what you're asking, right? Then yeah, it will go to the left. Right. If your reaction had the same number of gas molecules in reactants and products, then it will do nothing because the reaction can't do anything to change the pressure, right? So it will do nothing in that case. Okay? So let's do some more kind of examples of this, right? So we just talked about how pressure and volume, temperature affect these things. Okay? But here, just kind of showing pictorially how that pressure, volume, right? If I increase the volume, decrease the pressure, right? It's forming more B. Oh, sorry, this is increased volume, decreased pressure. It's going to form more A, right? Decrease in pressure, I was thinking increase A. Decrease in pressure forms more A, you got more space, you got less pressure. So the reaction is going to try to increase the pressure to compensate for that decrease in pressure you just did, right? If you increase the pressure, the reaction is going to try to reduce the pressure, right, back towards where it was. And so it's going to form more B here, right? Just kind of just representing that effective pressure. Okay. So in this chemical reaction here, right, we have these 4 different questions, right? In which direction will the equilibrium shift when each of these different things happens? So what direction is the equilibrium going to shift for this reaction if Cl2 gas is removed? I remove some amount of CO2 gas, which direction will it shift? Yeah, it'll shift to the right, right? I'm removing some amount of my product. So my chemical reaction is going to want to form more products because you just took some out. It's going to want to do what you did, so it's going to form more products, right? So your chemical reaction is going to form more products, and so it's going to shift to the right, right? It's going to form more products when I remove some CO2 gas. If I decrease the temperature, in that case, it will be to the left, right? And again, in this reaction, you can think of the temperature, right? This reaction is endothermic, right? It's got a positive enthalpy change. That means the temperature, that heat, is considered a reactant. And so I have my temperature plus PCl5 forming PCl3 plus CO2. And so if I decrease temperature, that's the same thing as decreasing the amount of a reactant. So the reaction is going to go to the left to form more reactant, right? And so it's going to go to the left to try to increase that temperature, okay? And so yeah, so a decrease in temperature is going to cause this to shift to the left, right? Now if I increase the volume in this reaction, which direction is going to shift? So in this case, it will not stay the same because I have one gas molecule here and I have two gas molecules here, right? Now I increase the volume in this system, right? Which means that there's more space, right? The pressure's decreased and there's more space. So my chemical reaction is going to form whichever side has more gas molecules, which in this case is the right side. So an increase in volume will shift this to the right, okay? Because I got more stuff, more gas molecules on the right. So an increase in volume means I'm going to form more gas molecules, right? Okay. And then finally, if I add some amount of PCl3 gas, in this case, it will shift to the left because I've added some amount of product. And so my chemical reaction is going to want to remove some of that product that you just added. And so it's going to form reactants, right, and consume products and shift to the left, okay? So again, to kind of sum up, right, one here was to the left, or sorry, to the right. Look, right, one is to the right, two is to the left, three was to the right, and four is to the left. Okay. Questions about this example? Right, if you're unsure about this, right, and you'll have more practice on the homework, right, you can review the questions and whatnot as well. But, you know, these are very common multiple choice type question, right, you can see on quizzes or exams, right, of here's a chemical reaction, right, how does it shift when you do this, right? So become familiar and comfortable with answering these questions, right? So here, we have another question, right? I have H plus ion plus IN minus forming HIN. I don't know what happened to the word green there. Me fix that. There we go. All right. 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 So, right, in this chemical reaction, the reactants have a blue color and the products have a green color. Okay. And so the question is, right, if I add hydrogen, or if I remove hydrogen ions by reacting them with hydroxide, okay, how I remove the hydrogen is actually irrelevant. But the main point in this problem, right, is I remove hydrogen ions, right, these H pluses. I remove some H plus. The question is what direction will the equilibrium shift? And what will the color of the solution be once it's done that? Right, so if I remove some amount of H plus, it will shift in what direction? It will go to the left, right? It removed some of this, so it's going to want to form some more. So it's going to shift to the left, right? Which means it's going to form more reactants, and it forms more reactants, which are blue color. That means the solution is going to turn blue. So D here, it's going to shift to the left, and it's going to form a blue solution. Okay. All right. Again, your equilibrium reaction, right, is going to try to undo what you've just done. Every one of these things related to the Shot-Lage principle is basically just the reaction trying to undo what you did, right? I removed H plus. It's going to try to undo that by creating H plus. And the only way I can do that is by having some of the products react to form some of the reactants, right? So it's going to shift to the left to form reactants, right? And then when I do so, I'm going to form more of these blue molecules, so the solution is going to turn more blue. Okay? Right? And again, here, this is just a reminder, right, for adding catalysts, right, it increases the rate at which equilibrium is achieved, but does not change the position or anything else at equilibrium, so it will not affect an equilibrium reaction and shift it in either direction. So questions about the Shot-Lage principle, these examples we just went over about things shifting to the left or shifting to the right.
So say on the previous slide,
Yep.
if you move green, it's going to shift to that side, right? So it's going to move to the right.
Yeah, so if I were to move HI, then yeah, it would shift to the right to try to form more HI, and then the color of the solution would turn green. Exactly. Mm-hmm. Other questions? All right, so that is it for chapter 15. Okay. So, right, reminder, starting Thursday night till Friday evening, you have a quiz on chapter 15. Okay. And again, the homework on chapter 15 is due on Monday. Okay. And next week, we will start talking about acids and bases. So wait a minute here for those on Zoom, if anyone has any final questions on Zoom before I close out the Zoom session. Right, yeah, and don't forget to turn in your participation questions on the table as you leave.
Question on
Yeah.
the participation grade.
Yeah.
Is that based on accuracy and participation or just participation?
It should be just participation.
Because I got a 75 on it and I only missed one participation paper, so I don't know how you.
Yeah, so I think, so when I calculated that grade, because weeks 5 and 6, there was an exam, so I combined that into 1 week, and by the time I calculated the grade, we finished week 6. So I only counted weeks 1 through 4, so the 4 days counted.
Okay.
And so if you miss 1 day, then that's how it was 75%. Now, I'll mention in future, I'm going to just drop a couple of days from everybody. So that, and if so what I should have done this time, but I didn't think about doing it when I calculated the participation grade, is that, you would have gotten 100% because I would have dropped 1 out of 4 weeks by now. I typically drop 2 to 3 weeks of just people missing for whatever reason they potentially miss and not really worry about it. So,
Okay. Well, thank you.
Yeah.
I just want to make sure.
Yeah. So your participation grade is all just on did you do it, and then if you did it correctly, which I've been keeping track of those points, then you can earn some extra credit towards the class.
Okay. Thank you.
Yeah. All right. So I see this question here. I wonder about the participation grade as well. Oh, thanks for answering that question. Oh, all right. Sounds good. Yeah, since I had only counted 4 weeks, that's why percentages look potentially low, even if you've definitely participated more than 75%, because it's just within the first 4 weeks of class. All right. So looks like there aren't really any other questions here. So I'm going to close out the Zoom session. And I'll see you guys on Monday.